So we're here today to present to you chapter 12.2, which is the wave-particle duality by Drew and Kyle.
So today, before we start, it is recommended that you guys look back on our lecture episode 347, in which we talked about 12.1, and with that, you're able to have a bit more background knowledge on this chapter, allowing you to understand what we talk about in further detail.
So basically what happened in the previous lecture is we discussed how photons act like particles with a given energy and momentum. But we also know from the previous unit that photons also experience wave-like properties. So what we do in this chapter is we're going to show how quantum theory basically brings together the two viewpoints of electromagnetic radiation exhibiting wave properties as well as particle properties.
So let's begin. We start off with the particle nature of electromagnetic waves. Zing-a-ling-a-zing.
So basically, the relationship between a photon and its electromagnetic wave can be thought of as an electromagnetic wave acting as basically a guide. I'm just going to refer to electromagnetic wave as EMW. So electromagnetic wave acts as a guide, and this predicts the probable behavior of the photon. For those of you who took chemistry, you've heard of Heisenberg's principle. This is basically the same thing, how EMW will determine the chance a photon will be at a certain position in space at a given time. And quantum theory assumes that a photon has a probability of being in any position, but the probability varies. For instance, in a region where the amplitude of the electromagnetic wave interference is greater, the probability of finding a photon will be greater. But the vice versa is also true, where if the interference is less, the chance will also be less. And this is why on nodal lines, the resultant amplitude is 0. And since the amplitude is 0, that means there's in fact a 0% chance of finding a photon. And now that we are in the 21st century, we can conduct photon experiments with much greater speed and sensitivity using an object called a photomultiplier. And so, as I said in the beginning, this chapter is about the wave-particle duality. So what the duality is it's the property of electromagnetic radiation that defines its dual nature of exhibiting wave-like properties as well as particle-like characteristics. But we cannot assume both at the same time, and this is what came to be as the principle of complementarity.
Robitussin.
So what this long thing, principle of complementarity, basically means is that to understand a specific experiment, we can't use both theories, the wave theory and particle theory, at the same time. We can only use one at a time. And this was decided by Niels Bohr. So generally when light passes through a medium, its behavior is best explained using the wave theory. But when light interacts with matter, its behavior becomes more like a particle.
So now we go on to the wave nature of matter. So we take a blast in the past, 1923, where we look at the scientist Louis de Broglie.
Broccoli? Psh. God, we ain't talking about vegetables, we're talking about Louis de Broglie.
Are you sure?
Where did you get that from?
Well, we're talking about science, and science is pretty dangerous. Should we cut?
Nah, keep going.
Okay. So now we talk about de Broglie. De Broglie proposed that the momentum of a photon can be given by the equation momentum is equal to Planck's constant over wavelength. And with this, he showed that the momentum could be expected to have an associated wavelength, which is also seen through the equation. Then, he suggested that it could also be determined through the Compton relationship, in which he stated that the wavelength is equal to Planck's constant over momentum which is then broken down into Planck's constant over mass by speed or velocity, depending on what you're looking at. And of course, the mass is a non-zero. And now, folks, we're back to another episode of Mr. Chintani's Example Questions! So, class, let's begin with today's example question. What is the wavelength associated with a 1,000 kilogram ball moving at 19 meters per second?
But sir, that's only one sig fig.
Okay, let's change that. 0.10 kilograms. And I promise you, that's my only mistake for today. So let's start. We know that the wavelength is equal to Planck's constant over momentum, which is then equal to Planck's constant over mass by speed. So then we can break this down. We know that Planck's constant is 6.63 by 10 to the negative 34 joules per second over 0.10 kilograms multiplied by 19.0 meters per second. And then, can somebody give me the answer, please?
Wait for it. Wait for it. Wait for it. Alright, I got it, sir.
And what is the answer, young boy?
3.5 times 10 to the negative 34 meters.
Ta-da!
Sir, I said 3.5, not 3.4.
My second mistake for today. And I'm pretty sure that's the answer. And that's it for today's episode of Mr. Chintani's Example Questions!
So now we'll be talking about matter waves. So in this section, we talk about quantum mechanics. And what quantum mechanics is it's basically the mathematical interpretation of the behavior and composition of matter based on the wave nature of the particles. So what this means is basically how we interpret particles to act. And the principle of complementarity applies to radiation, but also applies to matter as well. And so ordinary objects, like a baseball, also have associated wavelengths. But the problem is these wavelengths are very short and very small. And this is why they avoid detection. And so we tend to see, we don't see them act as a wave, rather we see them act as particles. For subatomic particles, the wavelengths are still very small, which makes detection challenging, but detection is possible, which is why we can see that electrons move in a wave-like pattern. And matter waves do not carry energy, rather they predict behavior, whereas particles carry the energy. And so the wave-particle duality exists for both matter as well as light. And this basically reinforces Einstein's theory that mass is interconvertible with energy with his equation of E equals mc squared. So an application of wave-particle duality would actually be electron microscopes, where the resolution of an ordinary microscope is limited by the wavelength of the light used. So there are three types of microscopes.
These three types are the transmission electron microscope, a type of microscope that uses magnetic lenses fashioned from circular electromagnetic coils, creating strong magnetic fields. Secondly, there's the scanning electron microscope, a type of microscope in which a beam of electrons is scanned across a specimen.
And last is the scanning tunneling electron microscope, which is a type where a probe is held close to the surface of a sample, and basically the electrons tunnel between the sample and probe, which creates a current.
And folks, that's all for today's lecture, and please look forward for the others. Good day. I woke up in a new Bugatti. I woke up in a new Bugatti. I woke up